talks about single degree of freedom system, which is a basic fundamental concept in structural dynamics. So let us start with structural dynamics. What is structural dynamics? It is the structural analysis methods, a set of methods for analyzing the stresses and displacements developed in a structure when it is subjected to time varying force. The time varying force means dynamic loads. Okay, so this is an extension of structural analysis what we have dealt in previously. So in this structural dynamics, we have different types of approaches. There are two major types of approaches which are deterministic and stochastic. So if we say deterministic, we can understand that the closed form solutions are available. Whereas stochastic includes that the probabilistic methods of estimation of loads, it can be estimation of loads or it can be estimation of displacements. So it can be anything. So in this lecture, we will deal only about the deterministic approach of solving time varying problems. And also there is another limitation that we will discuss only the structural dynamics, only the structures part, not any other form of solutions. So deterministic approach will be following. That means you can expect closed form solutions. Now let us further discuss about what is dynamic load. So in dynamic loads, that is the type of load of which its magnitude, direction and position varies with time. So there are three parameters in that. One is the magnitude that changes with time. So every time step we need to define the force. It is unlike any other static force which we apply in whole of structural analysis, whether it can be through slope deflection equations or moment distribution equations or Carney's method, whatever we use. Everywhere we are accustomed to not time dependent forces, they are static forces. Now in this lecture we will deal only the dynamic forces which are varying every time with time. Now what is the major cause of time varying forces? The major cause is because of earthquakes and blasts. So earthquakes are time varying force. Earthquake occurs in a 1 minute or max 2 minutes of time. So in every time step, if you divide the time complete 2 minutes, that is 120 seconds, we can estimate that for every second we can measure the force that is actually applied on the structure or induced on the structure. Now similarly the blast. So these two functions are not single force. They are a set of forces, or we can say an array of forces. So this array of forces. Now the challenge with us is how to solve our structural analysis. That means how to solve our structural behavior with respect to earthquakes and blasts, because they are not a single force but they are an array of forces. Now this, what happens if dynamic loads occur? So it results in lateral vibration in the structure. So this is another major concern. Now the force is time varying, that is anyways clear. But now another problem here is lateral vibration. Till now we have discussed about, if we are discussing about beams, columns, anything, we are discussing about the transverse loads. So if dead load is coming onto the structure, the beam is subjected to transverse load. So whatever the stress resultants that we have calculated, be it axial forces, shear forces, bending moment or torsional forces, everything is in terms of lateral displacements. Now this lateral displacement, the transverse displacement. Now the transverse results are the main cause. But in dynamic loads, the problem is lateral vibration is exerted on the building. Now that lateral vibration is the point of concern. Now for this, how to analyze the structure? What are the other parameters of structure that we have to define? Like structure has some characteristics or some parameters are representing the structure, like mass, and then you have stiffness, and then it may be like damping, that we will discuss further. But these are the main characteristics of mass and stiffness. Now this mass and stiffness, how do you define if we have to solve for lateral vibration? First, if we understand how much lateral vibration is coming, then we can counter that. How much what design we have to adopt such that the lateral vibration is under control. So all these parameters will come. Now, if we go to the next topic, which is degrees of freedom. So this is important because, as I have discussed already, that we need to define the characteristics of building or characteristics of structure in which direction, because force is varying in each direction. So what kind of force is coming onto the structure, because earthquake is not only exerting only lateral vibration, it is also exerting in all the directions. Like, if we divide it into 6 directions suppose, or 3 directions, which is transverse directions x, y and z. So in all the directions earthquake is likely to occur. Now what are the parameters that we have to define for the structure such that the vibration is exerted on the structure and the resultants are observed? So then we have to define the concept of degrees of freedom. So how do you define the degrees of freedom? It is the number of independent coordinates required to describe the motion of a system. So this is the minimum number of coordinates. So suppose if we take a pendulum, this pendulum, if we take the simple pendulum, okay, with the one mass, okay, this one, if we are discussing about this one, which is a single mass m, and then we have length of the simple pendulum, which is n. So in that case, if this is the case, then how are we going to understand, or how are we going to define the vibration? To define simple pendulum, the only thing that we have to define is where the mass is present, the location of the mass, right? So this location of the mass, what is the parameter that we can define? You can clearly see here, it is theta, right? So if you have theta, that means you can define the situation of the pendulum. In that case, if the mass is present here, then what are the forces that are getting developed in the length, in the thread or the string, whichever is placed here, right? That you can solve for. So what is more important is, what is the parameter that is actually available such that we can define the position or we can define the vibration situation of the structure. Okay, that is called degrees of freedom. So as it is written, like simple harmonic motion, which is to and fro oscillatory motion, in a simple pendulum requires 1 degree of freedom to define its motion, right? So only 1 degree of freedom is sufficient to define the situation of simple pendulum. But if we take another example of this one, this is a little complicated pendulum, right? So with two masses, we can say M1 and M2. In that case, how do you define the position of simple pendulum? In that case, we have one theta1 and theta2. There are two parameters required to define the motion of this pendulum, right? I think now you got an idea of how do you define degrees of freedom. So with this, if we talk about structural engineering point of view, okay, like degrees of freedom we can define like for any mass attached to that, and if we take only mass, because let us talk about mass, there are other parameters also that we can discuss later, but at least for this, you can define mass only in that 1 or 2 parameters, right? So in that case, if we talk about structural engineering, okay, in general there are infinite number of degrees of freedom in a structure. Okay, so if you take any point on a structure, if suppose this is a structure, any point in a structure, suppose this is one point, any point in a structure, how many directions you can define? The location of this or the position of that point can be defined in infinite number of directions, because this can be one, 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 any number of directions. That is infinite, right? We cannot decide upon. But structural engineering point of view, we are interested only in 6 degrees of freedom if we are talking about space frame. Like space frame, that means we have 3 frame of references like x, y and z. So we have x, y and z and the rotations corresponding to that, right? So in one direction you have one translatory motion and it can rotate in that direction about that one, and then 2, which is a translatory motion, and then you can rotate or rotate about that axis, about 2, which is 5, and then you have 3. Let us make it 6. Okay, so you have 3, third direction and the rotation about that axis, right? So this will be sufficient to define our motion. So in any firm structural engineering point of view, you can define the position of a point in any of these 6 dimensions if you are talking about the space frame. And if you are talking about plane frame, what is a plane frame? you have only 2 dimensions at hand. In that case, you can define only 3 ways. One is to, first one is for x direction suppose, and then you can say this is y direction and the axis about that point, right? About z axis. In fact, the about z axis. This is z axis which is coming out of the board, and then a rotation about that axis. So only 3 parameters or 3 degrees of freedom that we can define in a plane frame, right? So this will solve our problem of infinite degrees of freedom. Now, let us talk about kinematic indeterminacy. Why are we concerned about kinematic indeterminacy is, in structures, if we are narrowing it down to structures, we have already decided that infinite number of degrees of freedom are not required. Only 6 are sufficient in space frame and only 3 are sufficient in plane frame. Now, if we talk about kinematic indeterminacy, what is kinematic indeterminacy? Total degrees of freedom that are available after removing constrained nodes from the total degrees of freedom in a structure. So this is useful information, because how it is, let us see through this example. Now this is a plane frame, right? This is a plane frame. That means you can define only 3 degrees of freedom as given here, right? So at each and every node you can define that. In general, you can place a node anywhere. So you can place a node anywhere if you want, actually. But, so if you see any location you can place the node. But in structural engineering perspective, what we are more interested is the critical locations. What are the critical locations in a frame? The joints, because we have the maximum bending moments at the supports or at the joints, right? And even if it is for a beam or a column. So we need the critical locations, right? So why we need the critical locations? Because we need to design the building. If we are interested in designing the building, if we are designing for the critical ones, all the stress resultants in between these critical locations can be taken care, right? So that is our main agenda, to design a structure. So tracing it back, what we can understand is that we can have the critical locations. So we can define the nodes at the locations where we are interested in. So this is a plane frame where we are interested at only 4 nodes. Now in these nodes also, if we have to define kinematic indeterminacy, how are we going to do? We have to remove, suppose at each and every node we can define 3 degrees of freedom, right? So at each and every node we can define 3 degrees of freedom at all the 4 nodes. But in this case, at node 1 and at node 4, at both the cases, what happens is all the 3 degrees of freedom are constrained. That means these points are not allowed to move in any of the 3 directions, right? That is what is called a fixed support. Fixed support, right? If you are defining a fixed support, that means that nodes cannot move in any other direction. Okay, so all the 3 degrees of freedom are not possible at node 1 and at node 4. Now only we have to define at node 2 and 3. Now you see the total number of degrees of freedom that are available to be defined for representing this system is 4 into 3. Actually it is 4 into 3, which is 12. Right? So 12 degrees of freedom are required. But because of this constrained condition, at node 1 and 4, we are left with only 6, right? So only 6 degrees of freedom are required to be applied, to be used for defining the position of this frame, right? So the idea of degrees of freedom, and then why we have to go for kinematic indeterminacy is that we need to understand how many degrees of freedom that we have to define, such that we can understand the behavior of the structure, finally behavior of the structure, right? So that is the agenda. Now let us see the concept of stiffness. Why are we interested in the stiffness? Why are we interested in the stiffness? Because as I told you in the first slide about dynamic loads, the problem of dynamic loads, that means defining a force at varied time steps, okay, not at a single time step. That is one problem. The second problem is that if we go through that slide, we can conveniently say that this one, the lateral vibration, right? So the lateral vibration here results in a lateral vibration. Now, whatever we have dealt in, is all in terms of transverse vibration, right? Like beams, if you are doing some structural analysis, you are getting displacements in the transverse direction. Suppose beam is there. In that case, if beam is there, that is actually deflecting something like this, right? If it is a fixed beam, that means it is deflecting something like this. So whatever delta we are calculating, it is corresponding to this displacement. Now the whole problem is this frame is subjected to this kind of force. This or this. This is the vibration that is caused because of dynamic loads. Because the cause of dynamic load is earthquake or blast. Earthquake and blast are causing this lateral vibration. Now we need to define the lateral vibration. The problem of lateral vibration will lead us to the concept of stiffness. That means this stiffness will ask you, this stiffness is the property of the building in such a way that which will resist the lateral vibration that is coming from the forces, right? So let us define stiffness. It is defined as the force in a degree of freedom required to develop unit displacement or a rotation. Unit displacement or a rotation caused in an individual degree of freedom when displacement and rotation at all other degrees of freedom are zero. This is very important. Why we need to define this? Because we need to generate the stiffness at each and every direction or degrees of freedom that are available in the structure. Now, unit displacement, that means it is actually the force required by a structure to cause one unit deformation or rotation in a particular degree of freedom system or particular degree of freedom when all other degrees of freedom, the displacements and rotations are equal to zero. That is the understanding of stiffness. Right? So let us see through a small beam. Okay, let us see through a cantilever beam. Okay, we know this cantilever beam, deflection of a cantilever beam, which is PL cube by 3EI. Right? Now, this we have derived. The whole of structural analysis talks about this. Right? PL cube by 3EI. Now, PL cube by 3EI I can rewrite like this. So this term 3EI by L cube is nothing but the stiffness of a member, but this stiffness K is in the transverse direction. That means in this direction. Okay, this direction, because all our loads that are coming are in this direction and the resistance that is coming is something here. It may not be at the center, but it may be at here, but it is responsible, whatever parameter that is responsible for resisting this P, resisting this load is nothing but K, such that the displacement here is 1 unit. It can be mm, it can be centimeter, or it can be meter, but it is 1 unit. Okay, so that is called stiffness, but this stiffness, whatever we have defined, is in the transverse direction, not in the lateral direction. Now, the problem at hand is, how are we going to define the lateral stiffness of a building, right? So let us discuss about how we are going about that. Okay. So at each and every node we have 3 degrees of freedom required because it's a plane frame or plane you have x and y directions, right? If at all if it is x, it is x direction or y direction. Most of the cases the load is in the y direction, negative y direction, and your reaction is generated in the positive y direction. That is very clear. Now in a beam, axial forces are neglected. So what happens? There is no in a beam, what is happening? There is no this force, this degrees of freedom. Why there is no lateral degrees of freedom? Because when we are saying it is a beam, that means our axial forces are neglected, right? That's what is the assumption of beam. Why? Because beam is a flexural member. That means it is predominantly deformed in the flexural direction. That means transverse direction, right? So axial forces are neglected. That means even if the node is moving in positive x direction, we are not going to consider. It doesn't account to the complete structural response, right? So we are left with only two degrees of freedom at each and every node, right? Required, hence only 2 degrees of freedom are required at each node, which totals to around 4 degrees of freedom in the beam, right? there are two nodes, two at each node will result in 4 degrees of freedom for this particular cantilever beam, right? Now, let us see in detail how are we going to generate the stiffness matrix. Why it is matrix? Because we are now left with 4 degrees of freedom, not 1 degree of freedom. When there is 1 degree of freedom, then we have the stiffness as 3 EI by L cube. If we are understanding the structural behavior at 4 degrees of freedom, we are defining 4 degrees of freedom, then we are interested in understanding the stiffness at each and every degree of freedom, right? So then we are going to get a big matrix. Actually, if we can see, the stiffness matrix will be of the size. The stiffness matrix will be of the size because there are 4 degrees of freedom. We are interested, or we will be getting 4 by 4 matrix, because as we have defined the stiffness, like we have discussed about the definition of stiffness, which is the force required to cause 1 unit deformation in 1 degree of freedom when all other degrees of freedom are 0, which means this one. So there are 4 displacements. When we are defining 4 degrees of freedom, there are 4 displacements. In 4 displacements, 1, 2, 3 and 4, we, as per the definition of stiffness, if we need to get K11, which is stiffness in degree of freedom 1, if we have to get that, what we are trying to do? Apply unit deformation in 1 degree of freedom and all other degree of freedom, we are left with 0. Right? So with this condition, what is happening to the beam? We are discussing about displacement when it is applied. U1 is 1. Right? So when U1 is 1, that means displacement in 1 degree of freedom is one unit. In that case, what is going to happen? Let us discuss about how the structure is going to respond with this 1 unit displacement. Right? Why, if 1 unit displacement is provided in 1 degree of freedom, what is going to the structure? What is going to happen to this beam, if we say? Now, because this is a rigid joint, right? All the joints in a plane frame are rigid, right? This is what is the assumption that we are going forward, and that is the reason why we are resulting in shear forces and bending moment at the joints, right? And the whole moment distribution method or Carney's method is being developed because we are actually interested in rigid joints, right? So now in this rigid joints, what is going to happen? Unit displacement. What is going to happen in the beam? Because it is a rigid joint, it has to ensure 0 rotation at that node, right? At that node, 0 rotation is required. If 0 rotation has to happen, what should get developed? Anti-clockwise movement has to get developed such that this doesn't fall down. Okay, the dotted line indicates the imaginary displacement that is going to happen in the beam. Now this dotted line shows that it is trying to pull down and make it a straight line, right? So in that case, an anti-clockwise movement will help in ensuring 0 rotation, right? It is hooking like this. So this 0 rotation is actually ensured. So it is in the direction of 2. Then at node 2, which is in the direction of 4, what is going to happen? Even this joint is a rigid joint. It might not be fixed, but it is a rigid joint, right? So if it is a rigid joint, it also has to ensure 0 rotation. Now if it is a 0 rotation, what is going to happen? This has to develop a moment such that the 0 rotation is ensured at this node, right? So this is also in the direction of degree of freedom 4. Now on a beam, the complete rotation or the moment that is being developed is anti-clockwise, right? Anti-clockwise moment is being developed at degree of freedom 2 and degree of freedom 4. For the beam to be in stable condition, what has to happen? A clockwise moment has to develop in such a way that counters the anti-clockwise moment. For that to happen, we are providing with with two forces which act as a couple and divided by a distance of length of the beam, L, suppose, right? Length of the beam. Now this is a couple that is actually creating the clockwise moment to counter the anti-clockwise moment, right? Now let us discuss about the values of each one, values of moments or forces that are developed in each degree of freedom, right? So we know the concepts of slope deflection equation. Now slope deflection equations, we have derived that what is the force required in causing a moment if far end is fixed or far end is rigid, right? So if we solve those equations, slope deflection equations, we will result in this 6 EI by L square, right? It is actually 6 EI by L square into theta. If theta is not equal to, into displacement, I mean to say u, into u. If now u here is, that means displacement is unit. So we are getting value of 1, right? So this is equal to the moment that is developed in degrees of freedom 2, because the far end is fixed, is 6 EI by L square. At this node also the same conditions apply, because this joint is also rigid and this place is also causing 6 EI by L square. Now the total anti-clockwise moment that is coming here is 12 EI by L square, right? Now 12 EI by L square has to be resisted by a clockwise moment that is being developed by the couple. And how we are calculating moment due to couple is 12 EI by L square divided by L. That means length. Then what you get? This is the force that is actually coming here, right? So the force required in this direction to cause unit displacement is equal to the couple that is the moment that is developed at this location divided by the length of the member, because these two forces are acting as a couple to resist this anti-clockwise moment, right? So this force is also 12 EI by L cube. Now let us discuss about sign convention. When we have discussed previously, we have one node. We have defined the degrees of freedom like this. This is 1 and this is 2, right? In the previous slide, we have seen that the degrees of freedom are defined like this. Positive y direction and anti-clockwise movement are considered as positive. Now in that case, this is a positive force. So there is a positive 12 EI by L cube. This is a anti-clockwise movement which is positive. This is the sign convention that we have considered. So this sign convention is actually being applied here. So this is 6 EI by L square. And then in direction 3, what is going to happen? Because we are getting a clockwise movement, this is a couple that is getting generated. So this has to go downwards. And this is resulting in a negative sign, right? And this is again in the 4 degrees of freedom. Again it is 6 EI by L square, right? So this is all about 1 degrees of freedom. Now what we have got is this one. K11, if we are saying this subscript, if we are understanding what is subscript, K11 indicates force required or force developed in degrees of freedom 1, this one. So we can say Kij. So how do you define Kij? Is the force estimated or calculated in ith direction due to displacement in jth direction. So J is actually discussing about displacement and I is discussing about force or moment. Similarly, displacement or rotation, both, right? So Kij, this is the notation for the stiffness. Now K11 indicates force required in degrees of freedom 1 when unit displacement is applied in degrees of freedom 1. That is 12 EI by L cube. Now force required in degrees of freedom 2 due to displacement in degrees of freedom 1 will give you 6 EI by L square. Similarly, stiffness or force required in degrees of freedom 3 due to displacement degrees of freedom 1 will result in minus 12 EI by L cube. The same thing that I have written here, right? So all these things, you see the second subscript is 1 because we have applied the displacement only in U1, okay, in first degrees of freedom. This is the stiffness due to displacement in U1, right? Now this will leave us the stiffness matrix. Then, if we go for U2, right, second degrees of freedom is the rotation, right? So the beam is tended to move like this. Now we cannot, we are saying, intentionally saying that rotation is 1. That means we are not ensuring the rigid joint. Whereas here, we are still ensuring the rigid joint where theta is 0, right? So now second degrees of freedom, this has to develop some moment in such a way that the displacement or the rotation is equal to 1 unit. That we have found out to be 4 EI by L through slope deflection equations, right? So through slope deflection equations, we understood that 4 EI by L moment is required to develop displacement or rotation of 1 unit, right? Now, from the same slope deflection equations, we also know that what is the carryover moment to the rigid joint, to the far end, right? To the far end, half of this moment is going to get developed, right? And the direction of moment will tell us how it has to restrain. Because it is a rigid joint, it has to ensure 0 theta, that means 0 rotation, and an anti-clockwise moment is required so that the theta here is 0. If it is a clockwise moment, it will actually blow up, right? So that is not possible. Theta has to be 0. So there should be an anti-clockwise moment with a value of half of the far end moment, right? So these two are clear. Now coming to the verticals. So we are discussing about the case 2, where we are discussing about the unit rotation in degrees of freedom 2. So with this, we have resulted in getting a moment of 4 EI by N. And the total anti-clockwise moment that is developed is 6 EI by L. So in 6 EI by L, now we have, similar to the previous case, the total anti-clockwise moment has to be resisted by a clockwise moment which is equal to 6 EI by L, and hence the lateral forces or the transverse forces that are required are 6 EI by L by this distance, level arm distance, right? So 6 EI by L by L. This will give us the force required in degrees of freedom 1 and 3 to counter the anti-clockwise moment that is being developed, right? This is anti-clockwise moment that is being developed because of the rotations in 2 and 3. And then in degrees of freedom 1 and 3 are resulting in 6 EI by L square, right? So the similar way we can formulate the stiffness matrix, right? This is a vertical row column in the matrix where K12 gives us the stiffness or the force required calculated in degrees of freedom 1 due to displacement in degrees of freedom 2. That is equal to 6 EI by L square. That we have formulated here. Right? Similarly, we can formulate the other ones also. Now, let us go to case 3. In case 3, the third degrees of freedom, the displacement in third degrees of freedom is given, and this degrees of freedom will create some moments that are developed, right? So first, for this to happen, you have to pull it in degrees of freedom 3. If you are pulling in degrees of freedom 3, what is going to happen? This wanted to become as a straight line, but because this joint is rigid, you need to ensure a rotation, right? So that is a clockwise rotation, right? That is a clockwise rotation that is coming in this direction, such that this is actually not being not having a rotation of theta. Here theta should be 0, right? So to ensure theta 0, you need to develop a moment which is equal to 6 EI by L square. This is coming again from the slope deflection equations. Now, in the other direction, we know that it also should ensure theta equal to 0. So it also develops a clockwise moment to counter that straight line path, that imaginary line straight line path, and then that is equal to 6 EI by L square, right? When the total rotation or the moment that is being developed internally is clockwise moment, the the vertical forces should develop an anti-clockwise moment. From the couple that is being formed, that is separated by a distance of L, right? So that is 12 EI by L cube, because 6 EI by L square by L will give you the force. Now this is causing an anti-clockwise moment, right? Similarly, we can formulate the column matrix, right, where K13 is force in degrees of freedom 1 due to displacement in degrees of freedom 3. Now this is the case, displacement in degrees of freedom 3. Similarly, the other cases also, right? So with this, we have completed 3 degrees of freedom. Now the last case is that degrees of freedom 4. Now rotation in degrees of freedom 4, U4 is equal to 1. This requires 4 EI by L from slope deflection equations to ensure unit rotation at degrees of freedom 4. Because of this, there is a carryover moment that is developed as 2 EI by L in the degrees of freedom 2, that too in anti-clockwise direction, so that this rigid joint will have 0 rotation. Because anti-clockwise moment is being developed completely because of the moments, we need to develop a clockwise moment with the couple, right? The couple separated by length L, right? So the total moment, anti-clockwise moment that is getting developed is 4 plus 2 is 6 EI by L, and hence clockwise moment should come 6 EI by L square, right? Similarly, we can formulate the stiffness column, right? Stiffness matrix with a column matrix, right? K14, which is force in degrees of freedom 1 due to displacement applied in degrees of freedom 4, right? So this is Kij. Now here we have formulated that one. The total one looks like this. So you have K formulated as K11, K21, K31 and K41, right? So this column is completely represented by displacement 1, U1. U1 is non-zero, that means U1 is 1. Then you get a column matrix. Then K1, 2, which is displacement in the direction of 2, U2, and force in degrees of freedom 1, degrees of freedom 2, degrees of freedom 3, and finally degrees of freedom 4, right? So this is K42. Then you have K13, degrees of freedom 3, similarly, and then you have K14, which is force in direction 1, degrees of freedom, the displacement in direction 4, right? This constitutes a stiffness matrix. Now let us come back to the stiffness, the requirement of stiffness. Why are we interested to develop this stiffness matrix? Because previously when we are performing static analysis, we require only one stiffness, which is the lateral stiffness. Because our loads are in the lateral direction, we need the stiffness of the structure to be in lateral dimension, which is actually counteracting the forces. But in the case of earthquakes or blast, which causes a dynamic force and lateral vibration, right? Dynamic force and a lateral vibration when we are talking about structures. Dynamic force and lateral vibration, what we need to know is, we need to know the stiffness in all the directions possible at a particular node, so that we can study what is the force, what is the effect of force that is coming onto the structure in lateral direction or transverse direction, any direction for that matter, right? So that we have achieved. Now let us move further. Now let us discuss about the single degree of freedom system. Now what is single degree of freedom system? Now actually, as I have told you, earthquake or blast is actually causing lateral vibration in the structure, right? Suppose this is the structure that we have, a plane frame or a space frame, right? Building can be idealized something like this. There might be, the plan of the building we have not detailed it clearly, but suppose we consider a rectangular plan, okay? Rectangular plan of the building with only one story. If we understand that, we can understand the bigger complicated systems. Now, if we are understanding about the single story building with a very box structure, that means a regular plan, a lateral force is being developed or being applied on the structure, right? This is P. Okay, so this P is nothing but the force applied on the structure. Now, how that force is applied is because of earthquake or blast. Now, let us discuss about earthquakes only. because blast is like impulse kind of loading that has separate characteristics. But let us discuss about simple loading, which is earthquake, right? When compared to blast, earthquake is simple loading. Now this force is being applied on the structure. Now whether that force is applied or induced, that we will discuss later. But as of now, let us understand that P is applied on the structure. Okay. So our assumption is P is being applied on the structure. Now what is going to happen in the building? That is what we wanted to understand. What is the approach with which we are going to do? So let us take some assumptions. Okay. Roof is infinitely rigid. What does this mean? Roof is infinitely rigid means all the four nodes at the top are going to move in a same plane with the same displacement. Okay. Suppose if we are finding out the roof, something like this, and you are applying force in this direction, that means it will not go like this. It will go only like this, right? So each node will have its own, there is no internal deformation in the beam. Okay, there is no axial deformation in the beams. That is the meaning of roof is infinitely rigid. Okay, infinitely rigid. That will solve from problem. So this is actually called diaphragm action. If we say this is called diaphragm action, like that means this is actually moving together. The roof is moving together. There is no internal deformations inside the roof. Now second assumption is total mass of structure is lumped at the roof. Now the second assumption is, suppose because we have roof and then we also have beams there, right? The total load of this particular structure is majorly concentrated at the roof, right? Most of the load is concentrated at the roof, except for the walls and the columns. Most of the load is being applied at the roof. Now, for suppose for idealization or for simplicity sake, we are putting all the mass only at the roof. Okay, that is what is called M. Like this is the responsible parameter. This is the lumping of mass, right? All the mass of a roof and the mass of beams along with the mass of floor all put together along with columns and walls all put together at the top. Okay, this is the lumped mass. This is lumped mass. Okay, so this is lumped mass. This is not original mass. This is called lumped mass. Now, this lumped mass is applied with a load P. P, right? Now, axial stiffness of beams is infinite. This is actually linked with this one. Roof is infinitely rigid. Okay, axial stiffness of beams is infinite. What it means? That means internal deformations in the beam are not possible. Okay, we are restricting the internal deformations. Axially, internal deformations are restrained. Now, the fourth one is lateral stiffness of the structure is equal to lateral stiffness of all the columns. Okay, because beams do not have stiffness or beams do not have meaningful stiffness because it is infinite. That means infinitely rigid. There is nothing going to happen inside this. Now the stiffness of this total system is the responsibility of columns alone. Okay. So the lateral stiffness of all the columns. Lateral. Why are we talking about lateral? Because column is subjected to lateral forces. Beam is subjected to axial forces. Now axial stiffness, we are saying that it is infinite, right? But lateral forces that are being applied on the column are the responsibility of column itself. That means structure's lateral stiffness is equal to column's lateral stiffness. So this is the parameter K. Okay, how do I arrive at that? That we will discuss later. But K is the stiffness parameter. And then there is another parameter called damping. Damping is majorly caused because of the particle-particle friction, right? So with particle-particle friction, this material, whatever material it might be RC, it might be steel, whatever is there at molecular level, what happens is at particle-particle friction will be there. That will develop some form of resistance to whatever kind of force that is being applied, even if it is lateral force or it is transverse force. Whatever might be the force, there is some resistance offered from the material. That is actually accounted for in the damping, right? C. Now damping force is there and stiffness force is the responsibility of columns. Mass is there which is lumped at the top. This system is called single degree of freedom system oscillator. This is the basic fundamental idealization of a structure. This is also called inverted pendulum. Inverted pendulum model, right? So this is a structure with the whole mass lumped at the top, stiffness lumped at the columns and damping lumped at the columns, right? So this is the simple single degree of freedom system. Now if we discuss further how to analyze the forces that are getting developed in the simple pendulum or inverted pendulum model, right? We already know that D'Alembert's principle, it states that sum of the differences between the forces acting on a system and time derivative of the momenta on the system is 0. What is time derivative of momenta? What is time derivative of momentum? Momentum is mass into velocity, right? What is the time derivative of mass into velocity? It is mass into acceleration because mass doesn't have time quantity. So velocity which varies with time. Now time derivative of momenta is acceleration. So m into a, right? Sum of the differences between forces acting, right? The total force, if we say P, because we are talking about P, whatever force that is being applied, P and mass derivative of, like time derivative of momenta, which is mass into acceleration, is equal to 0. This is what D'Alembert principle. This is what is D'Alembert's principle. So we can say that P is equal to mass into acceleration, which is nothing but Newton's first law also, right? So what is this mass into acceleration? What is this force called? What is this force called? That means this is called inertia. Inertia force, right? So mass into acceleration is called inertia force. That means wherever mass is present, you are applying some lateral force. Then the force that is actually pulling back is mass times acceleration, which is called inertial force. So this one, okay, mass into acceleration. Let us come back to that again. Now, let us talk about inverted pendulum, okay. Inverted pendulum, right? In inverted pendulum model, mass is lumped at the top, stiffness and damping are lumped at the column. Now this is a form of single degree of freedom system. We can assume as if this is the frame, each column will have, is a plane frame, okay, in 2 dimension. Each column will have half of the stiffness k by 2 and mass lumped at the top. So columns are massless. Beams, columns, whatever mass of the column is actually going to the top. Beams and slabs, everything lumped at M. Okay, lumped at the roof, which is equal to M of the structure. Then C is represented by a viscous damper. This is called a damper. This is represented by C. Okay, this is what is called mathematical idealization. Okay, the mathematical idealization is a single degree of freedom system. Now from this, we can assume it as a mass spring damper system. Okay. Mass spring damper system. We can say that the mass is here M, which is present on 2 rollers which are frictionless. Okay, we assume that the friction from the floor to the mass is 0. Okay, so there is no resistance, that is additional resistance that is being offered at the floor. Then you have a spring. Okay, the stiffness, whatever we are saying, column stiffness, we can indicate it as a spring, like spring constant, right? Stiffness is nothing but the spring constant. So this has a constant K, which is equal to the stiffness of the structure. And then the damper, okay, which is representing the damping in the system. So the damping is intermolecular friction, right? This is an idealization of mass spring damper system. This mass spring damper system is applied with a load or dynamic force P, which is varying with time, P of T. This is called P of T, which is P, that is a force that is varying with time. If you are pulling like this, the forces get developed in stiffness as well as damper, right, in both the cases. Now this will also cause a displacement U. Because force is time varying, the displacement should also be time varying, right? Here, what is more important is this M, K and C. These three are called system parameters. System parameters. That means mass, stiffness and damping are given if the system is fixed. Right? If system is changing, these three parameters vary. Okay? Now force is coming from external forces, external sources. And this is the response, U or displacement. This U also includes rotation, that is little complicated, but let us talk about U, which is displacement side, which is varying with time. Now P is external load, U is response, M, C, K are called system parameters. Right? Now with the system parameters, can we talk about free body diagram? If we are talking about free body diagram, now as I told previously, if mass is present, according to D'Alembert's principle, what is going to happen? Inertia forces are going to develop. What is inertia? Which is mass times acceleration. Now acceleration can be represented like this. U is displacement, U dot, which is du by dt. This is velocity, U double dot, which is du square by dt square. D square u by dt square. Right? This is acceleration. So we can represent like U double dot. Right? So now mass into acceleration, which is M into U double dot, is the inertia force. This is called inertia force. And this is called spring force or stiffness. And this is called damping force. Right? So this is the load force that is applied for every unit time step. Okay, P of T. This is causing a displacement of U of T, and then which is resisted by three kinds of forces. One is inertial force, spring force and damping force. Three kinds of forces. Mu double dot, Ku dot and Cu dot. From this free body diagram, we can develop an equation which is called dynamic equation of motion. Right? Dynamic equilibrium equation of motion. Anything. Dynamic equilibrium equation or equation of motion. Now mass times acceleration, stiffness times displacement, damping times velocity. Right? So mu double dot of T plus Cu dot of T plus Ku of T is equal to P times P of T. This is called a dynamic equilibrium equation or equation of motion. From this, we can also define types of vibration. Right? Through this dynamic equilibrium equation, we can also define types of vibration because we need simplifications to understand the system behavior, right? Structure's behavior. For that to happen, the total vibration of a system can be divided into two kinds. One is free vibration. The second one is forced vibration. That means if P is 0, okay, if P is 0, what is going to happen? Actually, this is hypothetical. Definitely if P is 0, but we need to understand in detail what are the system parameters, how they are getting affected with respect to the lateral deformations, right? U is there. Now what happens if P is 0? And then forced vibration, which is Pt, P of T is not equal to 0. There is some force that is developed. Now this is completely the simplification aspect. To understand the system parameters, free vibration is required. Once you understand the free vibration, then the force vibration can be easily understood. Now in free vibration also there can be two cases. One is undamped and damped. Damping, as I have told, it can be neglected sometimes and it cannot be neglected sometimes. So the most simplified understanding is vibration of a system in free vibration under undamped conditions, right? That is called, this is the simplest form of understanding, like simplest way of understanding. So if damping is 0, P is 0, then understanding the free vibration. So this is called undamped free vibration. This is the fundamental way to solve the equation. Undamped free vibration. Other things, the most complicated one is the vibration of system under forced vibration conditions with damping, right? Damped forced vibration, that is called damped forced vibration. So all these things we need to consider in resolving the equation of motion. Like this is the equation of motion. Now to get u that is displacement at each and every time step, we need to get in each case what will be the solution, right? This, as I have told you, everything results in a closed form solution, right? So we can discuss about the solution of this dynamic equilibrium equation in all the 4 cases.